My name is Aisha. I am a third-year PhD student from Nazarbayev University, and thank you so much for the organizers for giving me opportunity to give a talk today. So today I will be covering the topic on the glioblastoma. I will be talking about the traveling wave speed and the profile of the grow glioblastoma multiforme. And this is the joint work with my PhD supervisors, Professor Arda Kashkambayev and the young Professor Yang Kwang, and also the collaborators Vibinur Shupieva and Erika Rutter. So first of all, I will just briefly talk about glioblastoma since it was already introduced before, and then I will show the go-grow hypothesis, and then it will be followed by mathematical model and mathematical analysis and numerical analysis. So as Mark already introduced, this glioblastoma is one of the most complex, deadly, and treatment-resistant cancers. So usually this glioblastoma model develops de novo within 3 months. So it's really hard to remove surgically since it has finger-like tentacles that extend some distance from the main tumor mass into the surrounding normal brain tissue. And the treatment of this GBM includes the surgery followed by radiotherapy and the chemotherapy. The complexity of the treatments include even in the case of this broad removal, tumor removal, glioma tumors tend to regrow its 90% of the mass, and the heterogeneity of the drug delivery to the various tissues in the brain, and the glioma cells also tend to adopt immunosuppressive behavior. So here we have go-grow hypothesis, which says that cell proliferation and cell migration are two temporally exclusive events. So it says that cells either migrate or proliferate, and also they can periodically switch between this proliferative and migratory cells. So usually the tumor growth starts with the small amount of proliferating cells. So as it grows, the center of the cells become dead. So for now, we are not focusing on the dead cells. We are just focusing on the proliferative cells and migratory cells. But for our future work, we want to include these 3 types of cells that include proliferative one, migratory, and the dead cells. So here we want to investigate the spatiotemporal dynamics of the tumor growth. So for example, if we have to choose minimum model, like Fisher model, like in here, so this Fisher model is known to overestimate the GBM progression. So we say that alternatively, if we are dividing the cells into actually growing and going, it might be more accurate. So this go-grow framework, it's not only applicable to tumors, but also it's applicable for the general frameworks like expansion of the population, yeast growth, fire, since they expand similarly. So this is the general framework for the expansion of the population. So our research goal here is to extend this FKPP model into 2 population GBM model by considering these proliferative cells and migratory cells. And then we want to study how fast tumor grows and how it spreads. And after that, we want to validate our proposed model by in vitro data. And for our future work, we want to extend our model by considering not only these proliferating and migratory cells, but also the necrotic cells as well. So here our mathematical model that was first introduced by Stepien. She introduced the model of GBM growth for the dichotomous behavior of the motile and proliferative cells. So here we have the system of PDEs. For the first PDE represents the migratory cell population, which consists of the diffusion, net growth death rate, and the switches between M and P populations. So M population switching to the proliferating state, and the proliferating state switching to the migratory state. And also this second PD represents the proliferating cells that are consist of this net growth death rate and also the switches between M and P. And we also say the density of the total cell population, we say that it's T, which is the sum of these M and P populations. So for the net growth death rate in the model, we choose this exponential decay mu_m for the migratory cells and this general growth function. So where this mu is the death rate, g is the growth rate. And also for the transitions between m and p in the model, we take these general functions where this k1 and k2 are the transition rates. So here we assume that cell growth is fast if this total population is small, and cell growth decreases as total population approach this carrying capacity Tmax. And here we have accordingly these two conditions. And also we impose conditions for the transition functions. So here we say that the phenotypic switch from this proliferation to the migration one can occur in the nutrient limited occasions and also when the cell density is high. So oppositely, we say that these migratory cells revert to the proliferating one if it's in the location with the lower density. And here we have the general condition for the transition functions that here we say that ft is an increasing function and ft increases to 1, f0 is 0, and gt is a decreasing function, gt decreases to 0, is 0 at 0, g0 at 0 is 1. And for the specific transition functions, here we use exponential functions or Hills functions. So here, our model, we say that K2 equal to 0, which means that there is no transition from the migratory cells to the proliferating cells. And we say that this might be the reasonable approximation of the reality, since the cells are often forced to move due to this increased resource limitations as cell density gets higher. So then we substitute the net growth, death functions, and transition functions into the model, and we end up with this system of equations number 5. And then we start our mathematical analysis by finding the minimum traveling wave speed. So as you can see from here, the key parameters here is the growth rate, diffusion term, death rate, and the growth rate. And after finding this minimum traveling wave speed, we compare it to the Fisher-Kolmogorov's model speed. So here we see the two speed. As you can see here is we have 2, and here our model speed shows that this term is less than 1, since g is between 0 and 1. And as you can see, this FKPP model is overestimating this GBM progression. So another work here is from Dwayne Harris' work, where he uses this Fisher model and SUP model in order to show the progression of the tumor. So here in green, we have the initial patient data, and in red, we have the final patient data. So for their model, the ISUP model, they also use the 2 population model, for which they use the proliferative cells and the quiescent cells that are not moving or growing. They're just in the silent phase. So as you can see here, the Fisher model is really overestimating the growth of the tumor compared to this SUP model. So, and then we continue our mathematical analysis by finding this approximate wave profile, where we use this Canozas methods. And Canozas methods usually introduce this following rescaling. And after that, removing all these small terms, we end up with this system of ODEs. And then in order to find this approximate traveling wave, we have to choose specific functions. So here we choose for the growth function, we choose this logistic growth function. And for the transition function, we use this piecewise linear transition functions. And after that, we check numerically how they converge to each other. So in this traveling wave profile analysis, we find that this approximate traveling wave solutions converge almost immediately to the analytical solutions. So this is the work model when we use the piecewise linear transition function with the logistic growth function. And the second one is the same, but for the transition function, we are using exponential transition functions. So here you can see they're almost the same. And our numerical analysis starts with the experimental data that were taken from the Stein's paper. So in which they used the human astrocytoma U87 cells line. So it was implanted into the gel with a wild type receptor. And then after that, the resulting spheroids here were left to grow over 7 days, and then they were imaged every day. So as you can see here, we have day 0, day 1, when they start expanding, and then day 3, and then day 7. So from these images, we took 2 pieces of data. The first one is the invasive radius. The second one is the density profile at day 3. And after that, we choose the specific functions for the for the growth. We choose logistic one, and for the switch functions, for the first case, we choose the exponential transition function, and for the second case, we choose the piecewise linear transition function to just check how they will perform. So, and for the error function, we choose this equation where the first term represents the comparison of the invasive radius to the model, to the data obtained from the images and from the model. The second sum represents the comparison of the density profile at day 3 to the data and to the model. So the error analysis here revealed that the piecewise linear transition function and the exponential transition functions, they perform almost the same in fitting data. As you can see here, we have almost the same error here. And after that, here we have our numerical analysis. This is the case where we used our model with exponential transition function. This first plot shows the invasive radius, and the red dots represent the Stein's paper simulation, and the black dots represents the exponential data. So as you can see, it's not really good, but for the density at day 3, if we zoom in this part, we can see that it's fitting, say, like good. And for the second case, when we use the linear piecewise transition function, it's almost the same. So the invasive radius is not fitting really good, but for the second case, when we are checking the density profile at day 3, it's performing good. So this is the end of my talk. Thank you very much. So if you have any questions, please let me know.